The hillside looks wrong, not because of what's there, but because of what's missing. No sulfides, no metallic shine, just deep red crumbling earth bleeding iron into every crack. It looks exhausted, like whatever made this place important has already been stripped away. But that's the illusion, because this isn't where the story ends, it's where it finally becomes visible. Most people never realise that some of the richest gold systems on Earth don't reveal themselves through quartz or visible gold, but through decay, through destruction, through the complete breakdown of the very minerals that once locked the gold away. And that rusted, iron-stained ground, it's the aftermath of that destruction. A signal so subtle most people walk straight past it, without ever realising they just stepped over the remains of a gold-bearing system. What you're really looking at when you see strong iron staining isn't just iron. In many cases, you're looking at the ghost of sulfides. Minerals like pyrite and arsenopyrite, which originally formed deep underground in hydrothermal systems, carrying trace to significant amounts of gold within their crystal structures. In many cases, the gold isn't sitting freely in quartz. It's locked inside these sulfides at a microscopic level. Fresh unoxidized ore can look completely barren. You can crush it, pan it, stare at it under magnification, and still see nothing, because the gold is literally imprisoned inside the mineral lattice. Then time takes over. As those sulfide-rich rocks are uplifted closer to the surface, they enter a completely different environment. Oxygen becomes abundant, water starts circulating, and that's when the chemistry begins to change everything. Sulfides are not stable in these conditions. They begin to oxidize. The sulfur component reacts with oxygen and water to form sulfuric acid, which further accelerates the breakdown of the surrounding minerals. The crystal structure collapses. Iron is released and rapidly oxidizes into iron oxides like hematite, limonite, and goethite, those deep reds, yellows, and browns that stain the rock. And the gold? It survives. Gold doesn't oxidize under these conditions. It doesn't dissolve easily in these surface environments. So when the sulfide host is destroyed, the gold is left behind, liberated, no longer trapped inside a crystal lattice. It becomes free, sometimes as fine particles, sometimes reprecipitated slightly downslope, sometimes concentrated into pockets where fluid slowed down. This is what makes the oxidation zone so powerful. It transforms invisible gold into recoverable gold. This is why iron staining can be one of the most important indicators a prospector can learn to read, but only if you understand what kind of iron you're looking at, because not all iron is equal. Barren rocks can weather red too. Basalts often oxidize and produce iron-rich soils. Even sedimentary rocks can carry iron that has nothing to do with gold systems. If you chase every red rock, you'll waste a lot of time. The difference comes down to texture, structure, and association. True sulfide-derived iron, what prospectors call a gossan, often has a distinctive look. You might see boxwork textures, where cubic or irregular voids remain after pyrite crystals have completely dissolved out. You might notice a honeycomb-like structure, or sharp-edged cavities that don't match normal weathering patterns. These are negative spaces where sulfide crystals once existed. That's your first clue. Then there's silicification. Many gold-bearing systems involve silica-rich fluids, so even after sulfides are destroyed, quartz often remains. If you see iron staining intimately associated with quartz veins, brecciated zones, or silicified host rock, you're starting to stack evidence. Add in structural control, faults, folds, contacts between rock types, and suddenly you're not just looking at iron, you're looking at the surface expression of a hydrothermal system. And that's where the probability shifts, because gold doesn't form randomly, it forms in systems. If you can identify that a system existed, and that it carried sulfides, you've already done most of the work. The iron is just telling you that the upper part of the system has been exposed and oxidized. But here's where things get even more important. Not all of the system is oxidized. Below the oxidation zone, sulfides often remain intact. That's what's known as the primary zone, and it can host significant amounts of gold, but in a completely different form. Down there, the gold is still locked inside sulfides. It hasn't been liberated yet. Which means if you take that ore, crush it and pan it, you might get nothing. Not because the gold isn't there, but because you haven't freed it yet. This is where most people give up too early. They test a piece of fresh-looking sulfide ore, see no gold, and move on, completely missing the fact that they're holding refractory gold material. The system is still there, it just hasn't gone through the natural oxidation process yet. If you want to access that gold, you have to replicate what nature does, but faster. Roasting is the most direct method. By heating sulfide-rich ore to high temperatures, typically above 500 to 700 degrees Celsius, you drive off sulfur gas and break down the mineral structure. Pyrite and arsenopyrite decompose, leaving behind iron oxides and freeing the gold inside. What you're doing is artificially creating an oxidation zone in a furnace. Done properly, it transforms invisible gold into material that can be recovered through gravity methods. But roasting isn't the only pathway. Chemical oxidation can achieve similar results. Processes involving hydrogen peroxide, glycine systems, or even bioleaching use reactive solutions or microorganisms to break down sulfides over time. It's slower than roasting, but it can be more controlled and environmentally manageable at small scale. The goal is always the same: destroy the sulfide host without losing the gold. Because once the sulfide is gone, everything changes. Gold that was once locked becomes accessible. It can be panned, leached, or concentrated, and in many cases what looked like barren rock suddenly produces consistent fine gold. That transition from invisible to visible is entirely controlled by whether oxidation has occurred, which brings you back to iron. Iron is the surface signature of that transition. It's not telling you gold is here, it's telling you something much more valuable. That gold could have been here, locked inside sulfides, and those sulfides have been destroyed. It's evidence of a process, not a guarantee of a result. But when you combine that signal with the right geology, silicification, structure, favourable host rocks, the odds start stacking heavily in your favour. And this is why experienced prospectors pay attention to iron in a completely different way. They're not chasing the colour, they're reading the history. They're asking what used to be here, what has been removed, what conditions existed to form sulfides in the first place, and where is the boundary between oxidized and unoxidized material? Because that boundary, the transition zone between fresh sulfides below and iron oxides above, is often where things get very interesting. Gold can accumulate there. Fluids slow down, the chemistry changes, it's a natural trap within the system. If you can find that zone, you're no longer guessing, you're targeting. And that's the shift most people never make. They look for gold as a substance, the visible thing, something they spot with the eye. But in systems like these, gold is the last thing to appear. Everything else shows up first. The structure, the alteration, the sulfides, and finally, the iron that marks their destruction. So when you see that deep red ground, don't dismiss it, because you're not looking at something worthless. You're looking at the remains of a system that was once chemically active enough to carry gold, structurally open enough to host fluids, and reactive enough to completely transform itself over time. Iron is what's left when a system has already done the hard part, and if you understand that, if you can read that signal properly, you stop chasing random outcrops and start following the trail of something much bigger. Not just gold, but the process that creates it. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.